Welcome to the fourth episode of the Introduction to the 6502 Assembly Programming series. In this episode, we're going to be talking about the accumulator. The accumulator is a register in the 6502 that really is at the heart of the ALU. It's how almost everything works. And so understanding what it is and how it interacts with the instructions is vitally important to writing any assembly code in the 6502. Alright, we have our ish slide back from the very first episode if you went through that one. This ish slide is letting you know that I've taken some liberties in describing some of these situations that I know aren't exactly correct. There's some simplifications and generalizations that aren't completely accurate. But I'm doing this in order to get concepts across easily, and then we can talk about the specifics later once we have a base understanding created. So if you are familiar with the 6502 and you're like, this guy is lying, it doesn't work exactly like that, and you hop down to the comment section ready to, tell me exactly what I got wrong. Well, I put this little red ish in the corner saying, in places where I recognize where I got things wrong, and probably got things wrong elsewhere that I didn't recognize, and feel free to let me know. But anyway, I know there's some discrepancies, and it's intentional to facilitate some of the understanding. So with that out of the way, let's get started. The accumulator is often designated by the A name, and all it is a temporary storage location for data in and out of the ALU. So it's a storage place that the ALU can put data that it wants to operate on, and that can live temporarily or for a long time. So here in this example that we have a representation of the RAM on the device. And the ALU doesn't operate on the RAM directly for every instruction. For some instructions it can. For some instructions it can't. And we'll see why here in just a second. Let's say we want to do an addition operation. We want to add the value at address 1 to the value at address 3 and store the results into address 4. Okay? So we want to do effectively hex 56 plus hex 1 and store that result, which will be hex 57, here. Okay? Let's kind of get a look at what that would look like. In 2 sections ago, we in the introduction to computer architecture, we talked about operands, opcodes, and operands, right? And so this is the slide. I've kind of stolen it back from that section. So when we have an instruction here, that gets assembled into an opcode or an operational code and an operand, 0 or more operands, could be multiples, could be 0, into the program memory. So let's go back and look at this addition example and kind of look at what it might look like if we had to encode this into machine language. Well, we need an opcode to tell the ALU that we're doing an addition. We need to tell the ALU what numbers we're going to add together. So we need the address of this variable, the address of that variable. And then we need to tell the ALU where to store it, the result, which is this variable. So if we did all that, it would look something like this, right? If we wrote an instruction, it would be something like this: an add instruction with the first input, the second input, and then where we want to store the result. Then if we tried to encode that in machine language, it would look something like this. I just made up an opcode. That probably is the opcode for an add. And then we have the first operand being the first source, the second operand being the second source, and the third operand being the destination. And you can see that's a huge sequence of numbers for this instruction, pretty large. But it also raises a couple other questions. What if I want to add 3 things together? Right? Do I need another instruction that then takes 4 operands, 3 things and 1 result? What if I want to add 4 things together? What if I want to add n things together? Right? It's a problem that never ends. So you can't do math like this inside of a computer. It doesn't really work this way. And so let me show you how this actually works. What actually happens is that there's this temporary storage location called the accumulator. And this is the first instruction that we'll cover in detail in 6502. So we're starting to dive into covering actual instructions now. So the first instruction we'll introduce you to is the LDA instruction. And that is load the accumulator. And what it does is it loads the accumulator with a value from memory, at least in this example. So if we had an instruction that was LDA and gave the value 1, this is telling the ALU, go to address 1 and move that value to the accumulator. And here we have a register. We have the accumulator marked with A. And so it just copies the value from here, from RAM, to the accumulator. And that's what that instruction does. Okay? Next, and you see our friend Ish has shown up here, we'll have an add instruction saying add address 3. And what that is going to tell the ALU to do is go off and take the value at address 3 and add it to the accumulator, and then store the results back into the accumulator. All right. So this one said add here and then store the results back into the accumulator. This add instruction, like we mentioned before, I was going to start showing you when status bits are affected. The load instruction affects the n bit and the z bit. So if you load a 0 value, the z bit will get set. If you load a negative value, the n bit will get set. Let's look at the second half of that math operation. We didn't quite complete it. We did the addition, but now we need to store it back. And that's going to take a second instruction. This instruction is the STA instruction, the store accumulator instruction. What this instruction does is it takes the value in the accumulator and stores it into an address in RAM. So just the opposite of the LDA, load, store. And so we have the result of our addition sitting in the accumulator here, but remember we wanted to store it in address 4 over here. And so what we're going to do is we're going to have an instruction that does store the accumulator into address 4. And so that will take the 57 from the accumulator and go off and write it into address 4. And so this is the way that more complex operations are actually done in processors. Because you can see, if I wanted to do 10 additions here, I could load the first one, then say add, and just keep on doing add instructions, and then store the result. And so I can scale this as much as I want, and creates a flexibility that you don't get trying to encode things directly into instructions. And that's not universally the case, but for most of the instructions, that is the case. And that's what the accumulator does. It provides this temporary storage for the ALU to operate on before it stores something back into RAM. So it pulls things from RAM or ROM, operates on them, and then maybe stores them back. The store operation doesn't affect any of the status bits. None of those none of those change when you do a store. All right, in one of the prior sections, the computer architecture section, we talked about the difference between constants, literals, and variables. And here we're going to get a view into what that looks like. So prior, we said the LDA instruction was going to load the accumulator from RAM or from memory. Well, it turns out that the LDA instruction actually has a lot of different forms. And this is the second form. And I believe these are called mode of operations in the assembly reference that I use. Don't quote me on that, though. So what this LDA instruction does is it loads the accumulator with a literal value. So let's say I wanted a very specific value moved into the accumulator, but it's not a value that's over here in RAM. It's not one of my variables. I'm not copying a variable to an accumulator. I just want to load it with a specific value. The way we do that is by this type of instruction, LDA with a hash mark, and then the value that we want to write. And that value gets directly written to the accumulator. Now, if you remember, if we go back to this LDA when we looked at it, this has a larger operand because this is the address of the variable that we wanted to load into the accumulator. And when we executed this one, we got 56 in the accumulator because it's the value at address 1, which is 56. This one, so that's loading a variable into the accumulator. This hash mark indicates to the ALU, or translates into a different opcode actually, when it's assembled. And that different opcode, while they both say LDA in assembly, this LDA has a different opcode from this LDA. This is a load variable into the accumulator, and this is a load literal into the accumulator. So from the assembly, they look the same, other than this hash mark. And that hash mark is really important to understand, and that's what tells the assembler that this is a literal load instead of a variable load. Just like the other load instruction, it affects the negative bit and the Z bit when the load occurs. All right, in this section, I'm going to do a little lab. I'm just going to run through I'm going to run through slide versions of this lab rather than doing it live. So it'll be a little bit easier to follow since it won't be constantly moving around. I'm using a website called Skilldrick on GitHub that is an online 6502 emulator. So, I would suggest you go over to this website. We'll use this throughout the class to run some example 6502 programs. It's much easier to emulate over here than using any of the other emulators for very simple demonstrations. And the website is fairly easy to use. So this is the website. It just has some brief introduction information about the 6502. There's a lot of references that you can click on here and some great information about the 6502. So, go here, read this information. It's going to be much more detailed than my class is. But then down here, kind of in his introduction, if you scroll down, he's running through the same things that I'm running through, and he has a whole bunch of different introductions to 6502. But here inside of each of these sections that he has an online emulator where you can write a little bit of code, and it has an assemble button that when you click the assemble button, it does like we mentioned before. It takes the assembly that you've written, generates the machine code, and then you can run it. So if we click debugger over here, we can either click run and it'll run through all the code, or we can click step here, and one by one it will step through the code. And if we look, each of these instructions is going to, when I click step, is going to increment the PC. We haven't talked about the program counter yet, but we will in a little bit. But over here, you'll see the A for the accumulator, SP for the stack pointer, XY, PC. These are all the registers we talked about. And the last one, the status one, is right here. So these are the bit names, and here are the values of each of the bits. So anytime you change the assembly, it's going to break out. It's going to stop the debug session, and you're going to have to click assemble again, and then you can enable the debugger again, and then you can either run or step over these instructions. So I'm just going to do this one little operation here where I load this literal value, remember this hash mark, of 01 to the accumulator. So I'm going to hit step, and we'll see that the accumulator now has 01 in it. And over here you'll see the 0 bit is not set, it's 0, and the negative is also set. I'm going to go back here and change this to a 00, click assemble, enable the debugger again. You always have to enable the debugger after each assemble operation on the simulator. Then here I'm going to click step one time to run the first instruction, and you'll see the accumulator gets loaded with 00. But down here you'll see that the Z bit is set now because we loaded a 0 into the accumulator. The result of the last operation was a 0. So the 0 bit gets set. The N bit doesn't get set. It wasn't a negative number. And so you can kind of see in this emulator, step by step, you go down each instruction, and you can see the results of the accumulator. You can see the results of the status register. And you can also monitor a certain section of memory. If you click on this monitor button and tell it you want to, let's say, look at address 200 hex and length FF hex. And then whenever you hit step, it's going to show you the RAM locations for the range that you specified. And so you can watch the RAM change as you execute each instruction. So that's kind of a basic overview of how the emulator works. Now let's go back to the slides and step through this accumulator lab that I've created to show you a couple of different things. So why are we using this? Why are we doing a lab? And why are we using this platform? Like I mentioned before, it's easier than most platform-based emulators. Like if you're using a console emulator, it's much more difficult to debug. You kind of have to have some startup code that gets the machine running, and this emulator doesn't need all that. Two, this website has a fantastic amount of 6502 learning material, like I showed. So, besides just taking these classes, poke around on that website and learn more information there. The more you get exposed to the same information said different ways from different people, the more likely you're going to find something that sticks for you. All right, so working through the lab instructions here, feel free to pause the video at any point in time to do each of these steps and then unpause them. I'm not going to insert real-time delays waiting for you to do things. So step through these, pause the video as you need, and then unpause it. So I've given the website there. Go to the website, scroll down to the emulated portion like I mentioned before, and go ahead and just click on the Assemble button with the example that is natively there. And like we mentioned, this will assemble the code that's in the text window into machine code. When you do that, all the other buttons will be enabled, like we saw in the live demo that I did. Next thing we want to do is to enable the debugger. And you're going to do that by checking the debugger box. Once the debugger box is checked, you get access to some of the debug information as well as the step instruction, which will be important. Next thing we want to do is we want to enable the monitor, the RAM monitor. So this is going to show you the RAM values like I mentioned. And so go ahead and check that box. When you check that box, it'll create another window that will hold all the RAM locations on the next execution, on the next instruction that gets executed. For the RAM for this demo, we're going to want to monitor at address 200. And this is just part of the demo that's written here. It won't always be 200. It depends on what value, what address you want to look at. And the code that happens to be in this window is manipulating RAM addresses in the 200 range. So we're going to set the start address to 200. And this will show us RAM addresses 200 to 2FF when we run the program. Next step is to note the value of the accumulator. We haven't clicked run, we haven't clicked step yet. And so the accumulator value is currently set to 0. And this is the reset value of the accumulator on the machine. Now look at our first instruction. It's an LDA, load accumulator instruction, and it has the hash mark. So this is going to load a literal value into the accumulator. Go ahead and click the step in the debug pane. This will execute just one instruction in the assembly. And here we're going to note the value of the accumulator. You see the accumulator is now 1 because the instruction that we had was load a literal value of 1 to the accumulator. All right, let's look at the next instruction. I'll give you a second to ask yourself what you think this instruction is doing. All right, let's look down below at the RAM address at 200. It's a 0. Okay? Next thing we're going to do is click the step button one more time. And what you see is that the RAM address at address 200 now has a 1 in it. That's because this instruction is saying store the value that's in the accumulator to the RAM address 200. So take the value of the accumulator 01 and store it into address 200. And so it copied this value over here. All right, now look at the remaining instructions. Think in your head what they're going to do. Try to work it out in your mind before you click step through and see what they do. And see if you can figure out what each of them are doing. Once you've convinced yourself you know what they're going to do, click step 4 times and see if it matches what you expected. After you've run through that, I have an extra challenge here for you to do on your own that's not written here and is not just to follow along. I want you to go in and add code to the end of this assembly that will set RAM address 220 to the value of hexadecimal 33. And note that once you add your code here, you'll have to re-click the assembly button and step through the code again. And so when you get this done correctly, you'll see the value 33 here at the address 220. Okay? So this is the assembly that you would write to do that. Hopefully you paused and didn't just immediately see this and accidentally. Maybe I should have paused a little bit longer. Sorry, but this is the answer. So the first instruction is to load a literal value of 33 into the accumulator, and so you'll see over here that we have accumulator is the value 33. And then the second instruction says store the value of the accumulator into 220. And so that instruction, when it executed, loaded, copied from the accumulator to that RAM address. So there's no instruction in the 6502 that can directly write a value, a literal value, to a RAM address. You always have to go through the accumulator first. And that's it. That's kind of the introduction to accumulator. We'll see it used in a lot of different ways in future instructions, but it's kind of just a temporary scratch pad for the ALU to do operations on between loading and storing operations or data from either the ROM or the RAM. In the next section, we'll cover the next set of registers, and those are the index registers X and Y. If you didn't feel completely comfortable with the accumulator section, I would recommend that you go back through and step through those examples again before moving on to the X and Y. The X and Y instructions definitely take it to, or registers, take it to the next level of complexity from the basic operations we showed in this section. The X and Y are indirect references to RAM rather than direct references. Everything we did with the load instruction and the store instruction when using RAM addresses were direct access. We gave the RAM address that we wanted to modify or the RAM address that we wanted to load. When we talk about the X and Y register, we're going to be talking about indirect access or indexed access. All right, I hope you enjoyed that section. If you have questions, feel free to leave comments below, and I'll try to answer them. If not, if you know how to reach out to me on Discord, shoot me a question over there. And good luck. Have fun.